Alright guys, so we are back with another video that is going to discuss the tutorial of the thermal physics Newton's cooling law part, right? So this is simply a tutorial based on the Newton's cooling law principle. Alright, so let's get started with the first problem. It says 1 kilogram of water in a container is heating with a heater of power 1 kilowatt, right? So there is a 1 kilogram of water. That 1 kilogram of water is heated using a heater of power 1 kilowatt, all right? And then they are saying the temperature was increased from 27 to 47, right? So it was seen that the temperature of the water increased from 27 to 47, right? Within a time interval of 100 seconds. Within a time interval of 100 seconds. So if the heat capacity of the container is negligible, they're saying the container doesn't absorb heat, right? So if the container doesn't absorb heat, the average rate of heat loss to the surrounding, right? So here, if we consider this as the water column, right? So the heater supplies heater is supplying heat, let's assume Q1, right? So from that Q1, a part of heat is absorbed by water Q2 and a part of heat is released to the environment Q3, right? Uh, the heater supplies amount of heat Q1, water from that Q1, water absorbs a certain amount Q2 and releases a certain amount Q3, right? So here it is heat supplied by heater is equal to heat absorbed by water plus heat released to surrounding, right? So let us assume the heat supplied by the heater is what? We assumed it to be as Q1, isn't it? Heat absorbed by water, we assume it to be as Q2. Heat released to the surrounding, we assume it to be as Q3. So since they have given rates, I'm going to divide all the terms by T. Q1 over T is what? The power, right? Power. So Q2 is what? Q2 is the heat absorbed by water. All right. 1 kilogram of water, MC theta. C is 4200. What is theta? 47 minus 27. Temperature increased from 27 degrees Celsius to 47 degrees Celsius, which means the increase in temperature is 47 minus 27, right? So divide by the time. What is the time taken for this? It has taken 100 seconds. All right. So what is Q3 now? Q3 of course is what they are asking. This is Q3 over T. This is what they are asking. The rate of heat loss to the environment. T1 they have already given this to be as 1 kilowatt. 1 kilowatt means 1000 watt. So we have to simplify this, right? 4200 into this is 20 over 100, right? So 100 plus this, let's assume this is Q3 dot, right? The rate of heat loss. So you have to subject Q3 and simplify it. So in that case, you are going to get an answer closer. So let us go for the second problem, which says there is a sphere, a cube, a cylinder, and a thin circular disc. All are having the same mass and made out of the same material, right? Heated to the same temperature and then allowed to cool. Which of them cools fastest? Now this is an argument problem. You cannot use calculations to get the answers, guys, right? So you just have to get the answer argumentally, right? So you will have to make some assumptions and also to figure out this kind of a problem. All right. So here, if you see in this problem, of course, the second one, right? So there is first of all, there is a sphere, right? There is a sphere, and there is another, what, there is a cube, right? There's a cube, all right, and then there is also a cylinder. There's also a cylinder, right? And also a circular disc, right? A very thin circular disc. So in that case, we need to see which and made out of the same material, right? So which cools faster. So so these are going to have the same mass, m, m, same density, made out of the same material, same material. If they have the same mass, same material, same mass, same material, then they have the same volume. They have the same volume. So if you see the sphere, cube, cylinder, and the thin, they have told that this is thin, right? Thin circular disc, which will have the highest area. So volume is equal to area into perpendicular length. So this perpendicular length here is very, very small, right? Very small perpendicular length, perpendicular height, which means it has a very large area. It has a very large area. So when compared with the others, right? So it has a very higher area, right? Okay, now we have found circular disc. Circular disc has the higher area, right? So in that case, what happens is, we know what they're asking is the rate of heat loss, which is highest, in which is the highest, which cools faster, which cools faster. We know that dq over d theta is directly proportional to dt over d theta over dt. Like the rate of heat loss is directly proportional to the cooling rate, right? So also we know that dq over dt is Ka theta minus theta r. This is the rate of heat loss. So this is constant. All these are heated to the same initial temperature, and the room temperature is the same. So therefore we can say the rate of heat loss is directly proportional to the surface area of the objects. Now who has the highest surface area? The circular disc. Circular disc has the highest surface area. So therefore the rate of heat loss of the surface area is the highest. If the rate of heat loss of the surface area is the highest, then the cooling rate of the circular disc will be the highest. So therefore the fastest cooling is going to be seen from the circular disc. And then also if you simplify, I forgot to mention that if you simplify this previous question, we're going to get 160 watts, right? So yeah, let's know that as well. Okay. Right, guys, so let us go for the fourth question. So here it says an object is heated and allowed to cool. All right, so if the room temperature is 30 degrees Celsius and a rate of cool at 100 degrees Celsius is 4 degrees per minute, then they are asking us to find the rate of cool. Rate of cool means the cooling rate at 65. What they have said is the room temperature is 30 degrees Celsius. The cooling rate when the temperature is at 100 degrees Celsius is 4 degrees per minute, and the cooling rate when the temperature is 65 degrees Celsius is what? That is what the question is. All right, so let's move on. All right, sorry. So what they are saying is at okay, the room temperature is what exactly? The room temperature theta r is 30 degrees Celsius, right? So the cooling rate at theta equals 100 degrees Celsius is, the cooling rate means d theta over dt. This is the cooling rate. This is 4 degrees per minute, right? They are asking what is the cooling rate when the temperature is 65 degrees Celsius, the cooling rate, right? So for this, of course, we need to know the cooling rate equation. We will have to know the cooling rate equation. The cooling rate equation d theta over dt is equal to what? K theta minus theta r. Here K is a constant mc over Ka, right? This is a constant, simply a constant. So let us apply this equation for the first instance, right? For the first instance, if we apply the cooling rate is 4, K is a constant, the temperature is 100, right? So the temperature is exactly 100, and the room temperature is 30, right? 30. So in that case, this is the equation 1, right? So we need to find the cooling rate at 65. Even in that case, the constant is a constant, that's it's not going to change. The temperature of the object is, in that case, is 65, 30, right? So the second equation. So if we divide the second equation by the first equation, we're going to get d theta over dt over 4, right? K 65 minus 30 divided by K 100 minus 30. So this to this cancels, and if you simplify, you're going to get d theta over dt. The cooling rate is 2 degrees per minute, right? It's going to be 2 degrees per minute. This would be the cooling rate, right? So yeah, see, all right, okay, fine. Okay guys, let's go for the fifth question. So here what they're saying is the rate of heat loss when the temperature of an object is 60 degrees Celsius is 90 watts, and that of the rate that of means the rate of heat loss when the temperature is 50 degrees Celsius is 60 watts, right? So what do they say? Simply let us mark all what they are saying in the diagram. All right, okay. So there is an object which is at 60 degrees Celsius, right? When it is at 60 degrees Celsius, the rate of heat loss means dq over dt is 90 watts. And then they are saying when the temperature is 50 degrees Celsius, the rate of heat loss is 60 watt. When the temperature is 50 degrees Celsius, the rate of heat loss is 60 watts. Now what they are asking is find the room temperature. It's quite easy, right? So you need to use the rate of heat loss equation to figure this out. dq over dt is equal to Ka theta minus theta r, right? The rate of heat loss for the, let's assume this is the first instance, this is the second instance. So for the first instance, let us apply the rate of heat loss concept. The rate of heat loss is what for the first instance? 90 watts. K is a constant, A is a constant, K, A, constants, right? So K, it's the same object means K is constant. Same object means once again the area, surface area exposed to the environment is a constant. So what's the temperature in this case? First instance 60. We do not know the room temperature, first equation. And let's apply the equation for the second instance. So in the second instance, the rate of heat loss is 60. Ka is once again a constant. The temperature of the object is 50, theta r. It's the second equation. So actually guys, we need to divide the first equation by the second equation. In that case, what we are going to get is 90 over 60. Ka 60 minus theta r. Ka 50 minus theta r. So if we simplify, this to this cancels out, and we would get an answer for theta r as 30 degrees Celsius, right? I'm not gonna simplify it, guys. I guess you can verify it after simplifying it perfectly. All right, so this is it. Simply we applied the rate of heat loss equation for both these instances. That's only what we did, right? Okay guys, let us see what they are asking next. All right, this is done. Find the rate of heat loss when the temperature of the object is 45 degrees Celsius and 30 degrees Celsius. Find the rate of heat loss when the temperature of the object is 45 like when the find the rate of heat loss when the temperature of the object is 45 degrees Celsius and 30 degrees Celsius. When it is when the of course we know when the object reaches 40 degrees Celsius. Now when the object reaches 45 degrees Celsius, we need to find the rate of heat loss, rate of heat loss dq over dt. So once again I'm going to use the same equation. Dq over dt is equal to Ka theta minus theta r. In this case, of course, what we need to find is dq over dt. Ka is a constant, theta is 45, and this is 30, and this is the third equation. So what we are going to do is, maybe we are going to we could divide the first equation by the third equation. We can divide the third equation from the first equation, that is dq over dt over 90 is equal to Ka 45 minus 30, Ka 60 minus 30. This to this cancels out, and if you simplify, we could get dq over dt, the rate of heat loss when the temperature is 45, we will be getting something at around 45 watts. Yeah, it's going to be 45 watts. And what is the when the and then they further ask, when the temperature of the object is 30 degrees Celsius, what's the rate of heat loss? Actually guys, is there going to be a heat loss? No, because why? The room temperature is also 30 degrees Celsius. It's already cooled down to the room temperature. Therefore, there's not going to be any further heat loss. So therefore, in that case, of course, simply you can say the heat loss is 0, right? When the object reaches the room temperature, further, of course, there's not going to be any sort of heat loss. All right. Okay, cool, fine. So therefore, that is also done, right? All right. So let us discuss the seventh question, right? So in the seventh question, what it says is, so the sixth one is kind of a similar question as we have done earlier, right? So therefore, like, I'm not gonna discuss the sixth one. I'm gonna straight away go for the seventh question. It says, in a room where the temperature is 30 degrees Celsius, a body cools from 61 to 59 degrees Celsius in 4 minutes, right? So let us mark it quickly, right? So this is the seventh one, right? So the seventh question, so there is a body, so where the room temperature is 30 degrees Celsius, right? So this, of course, cools down from 61 to 59. It cools from 61 degrees to 59 degrees within a time interval of 4 minutes, right? 4 minutes. What they want is the same object, what is that amount of time that it would take for it to cool down from 15 to 49, 51 to 49, right? 51 to 49, 51 degrees to 49 degrees, right? So that they require the time actually. So to solve this kind of a temperature reduction problem, right? So we will have to use use the equation for the cooling rate. You actually know, right? So we have two equations, that is dq over dt is actually equal to Ka theta minus theta r, while the cooling rate equation d theta over dt is equal to Ka theta minus theta r, right? So out of these two equations, what we need to use is this equation, the cooling rate equation, because since this is a temperature reduction problem, so I'll consider this as the first instance, right? I'll consider this as the first instance and this as the second instance. For the first instance, I will apply the d theta over dt Ka theta minus theta r equation. So d theta over dt is what in the first case? What is the temperature difference? 61 minus 59. 61 minus 59. What's the time taken? 4 minutes. You need to convert into seconds. K. And no need to convert it into seconds. We need the answer also in minutes, right? So I'll leave it as it is. What is the temperature of the object? Are we going to take it as 61? No, we can't take it as 61, right? So as the temperature of the object, we cannot take it as 61. We need to take it as the average of these two temperatures. We do not know whether it is in 61 or 59. It's in between, right? So therefore, we'll have to take always as the temperature of the initial temperature of the object, the average of this and this. Very careful, right? Very careful in this point, because like most of you guys make mistakes here. So it is 61 plus 59 over 2. What is the room temperature? 30. So this is the first equation, right? This is the first equation. So let us consider the second instance. In the second instance, the temperature reduction, the object needs to cool from 51 to 49. So 51 to 49, but I do not know the time taken. I do not know the time which it takes to cool down. So the constant is K. 51 plus 49 over 2 minus 30 room temperature. So simply to find the time, what we need to do is divide the second equation from the first equation. You are going to get 51 minus 49 over T into 4 over 61 minus 59 is equal to K 61 plus 59 over 2 minus 30. In the other side, K, K, this comes down, right? 1 over 51 plus 49 over 2 minus 30, right? You just have to simplify, right? It's not going to be very complicated, right? So like, although I have written it in somewhat of a longer form, like if you simplify it here itself, right? So it's nothing, right? It's pretty much of a basic simplification. So like you will have to figure the time out, right? So I'm not gonna simplify it right here and take up your time, right? So you'll have to simplify this. Definitely you will be getting an answer out of this, right? So okay, I guess that's fine with. I'll do a similar question as the seventh one, so that you will get a pretty you'll be pretty confident on what you've done. So let us discuss the seventh one, eighth one. It's also kind of a similar question. So eighth one, guys, if you see, it says a body cools from 50 to 49.9 in 5 seconds. How long will it take for the same body to cool from 40 to 39.9? Assume that the temperature of the surrounding, the room temperature is 30 degrees Celsius, right? So we'll see, right? 50 to 49 point. Okay, this is the eighth question. There is an object. Its temperature reduces from 50 degrees to 49.9 degrees, right? So the time taken for this is 5 seconds, right? The room temperature is said to be at 30, right? Is it 30? Yeah, 30. So it is 30. And then once again, what they're asking is the time taken to reduce the temperature from 40 degrees to 39.9 degrees. The time. The time. What they're asking is this time. So, right, what would we do in that case? So here also the room temperature is the same, right? 30 degrees Celsius. So we'll have to assume this as the first instance, these are the second instance, and proceed with, right? So for the first instance, let us apply the equation d theta over dt, k constant, theta minus theta r. What's the temperature d theta? For the first instance, d theta is 50 minus 49.9. 50 minus 49.9 divided by time taken is 5 seconds. Is equal to K. What's the temperature of the object in the first instance? It's not 50, it's not 49.9. It's 50 plus 49.9 over 2 minus, what's the room temperature theta r? 30. This is the first equation, guys. So also let us apply the equation for the second instance as well. Let's apply the equation for the second instance as well. So if we apply for the second instance, right, simply it's going to be So in the second instance, of course, the temperature difference is 40 minus 39.9. 40 minus 39.9 over the time, of course, I do not know. K, that is a constant. What's the temperature of the object uh, at that moment? We have to take it as the average of 39.9 over 2. And this, so we'll have to divide. If we divide, of course, the first equation and the second equation, k to k cancels and everything simplifies, and you will get an answer for t, right? You'll get an answer for t. You'll have to properly simplify it. I'm not gonna simplify it. All right, so this is how you do such questions, guys, right? Eighth one. As a final question, I will do the ninth one and wind up. Okay, so let's go for the ninth one. So in the ninth one, of course, what they're saying is when an object is allowed to cool freely, its temperature falls from 55 to 45 in 10 minutes and fall from 45 to 39 in the next 10 minutes. Find the temperature of the object after next 10 minutes, right? So this is, it's not a very complicated question. You'll have to use the same concept, right? The ninth question. Initially, there's a object, so its temperature was 55 degrees Celsius. It falls from 55 to 45. It cools down within a 10 minutes time, right? And then from 45 to what 45 to 39, it takes 10 more minutes. It takes 45 to 39, it takes 10 more minutes. So we need to find what will be the temperature after another 10 minutes. We need to find this temperature. So actually there are three cooling processes, right? This is the first cooling process, this to this is the second cooling process, this is the third cooling process. Why do we need to deal with all these like three cooling processes? Because like they have not given the room temperature as well, right? So this room temperature is also not known, this is also not known, right? So and also, when applying that, there's going to be a k value. That k value also is also not known. So therefore actually you are going to have three unknowns, right? So which means you will have to get three equations, right? And then you'll have to go for a simultaneous solving, right? So I'll consider the first first process, first cooling process. So we are going to apply d theta over dt is k theta minus theta r, right? So the first process is d theta is what? It decreases from 55 to 45, right? The time is 10 minutes, right? 10 minutes. K unknown, theta, what's the theta? 55 plus 45 over 2. We take the temperature of the object as the average of these two temperatures minus the room temperature unknown. First equation, right? Now we go for the second equation. So second process, the second cooling process, that the temperature decreases from 45 to 39 once again in 10 minutes. The k value is unknown. What do we take the temperature of the object as? 45 plus 39 over 2 minus room temperature. Do we know it? No. Second, let us consider the third process. The third process, if you consider the third process, guys, the temperature decreases from 39 to what? We do not know that. 39 to what temperature? That is what we need to find in 10 more minutes, right? So now we need to take this as 39 plus theta over 2 minus the room temperature. We do not know that. So guys, somehow this is a simultaneous solving. Like we have three equations, 1 2 3, three unknowns, k, theta r and theta, right? So three simultaneous three equations, three unknowns. We can find theta, we can find theta r, we can find k as well, right? So what we need is only theta. So therefore you'll have to simplify this and find theta. So I guess I'll wind the session from this point onwards, right? So we will discuss the rest of the questions in the tutorial session 2, right? So yeah, all right, thank you guys. See you with another video.